All right, question number 2. How do you find the domain and range of a rational function? So in my previous lectures or sessions, I covered what the domain and what the range of a function was, and I'll repeat it again. Okay, so let's say that we have a pool or a value of x values here. Okay, so out of all the real numbers, we have a pool of x values. Okay, we'll say this is x. All right, and let's say that we have a pool of y values called, let's just call it f of x. Okay, so the domain is every value of x that defines the function. Okay, so a function's primary purpose is to map one value to another through a set of rules, a set of axioms, or by a function kind of thing, right? So the domain is all the values of x that define f of x. Okay, so all the values of x that lead to f of x. So these values of x can be the whole real number set. It can be the integer set. It can be the natural number set. It can be expansive or very, very exclusive, depending on what our function is and what our function is describing. Okay, so we call this bubble, this red bubble, the domain. Okay, so from the domain through the function f to f of x, we have what we call the range, which is all the possible values of f of x of the function itself, and we call this the range. Okay. So the way that we usually find the domain of our function is by finding all the cases of x or all the values of x which do not define the function itself. And by doing so, we can write a concluding statement which will encapsulate the domain and exclude the ones that are not part of the domain. And there's a very neat trick of finding the range. Okay, so you guys can also think about finding the domain and range by graphing them visually and looking at the graph and saying where are some discontinuities, where is the graph leading, and what parts of the graph are excluded, right? So finding the range, you can just look at a graph and be like, oh, I see that this whole function is positive. That means the range is all f of all y greater than 0, right? You can say that. Another way to find the range is by finding the inverse function. Okay. Oh, that's blue. So by finding the inverse function, um, what's very neat about the inverse function is that the range of the original function becomes the domain of the inverse, and the domain of the original function becomes the range. So by finding the inverse function and figuring out its domain, we can find the range of the original function. Sometimes it's hard to find the range because you can't graph out the whole function itself, and most of the time we can't really figure out where f of x doesn't exist, I guess you could say. All right, so we're going to use this trick to solving this problem. So now let's address the problem itself. So how do you find the domain and range of a rational function? Okay, so if you were to graph out a rational function, this is what it would look like. And I'm just going to do a general view of the rational function here. So let's say that, oh, it's in gray for some reason. Okay. Let's say that this is x and the y-axis. So rational functions kind of look like this. Okay, so they have two sides to them, and they look like this. Okay, so there are parts of this graph where it's undefined. Okay, and we're going to try to figure that out mathematically speaking. Okay, so the junior tutor wrote here that a rational function is defined as a rational fraction where both the numerator and denominator contains polynomials. So that is technically correct. So we have, let's say, big f of x is basically the ratio of two functions. So f of x over g of x. Okay, and these functions can be whatever you want. Okay, in this particular example, the junior tutor said polynomials functions, and for a large majority of the mathematics you'll find in high school math, it's going to probably be polynomials. So we're going to stick with polynomials for now. Okay. So for a fraction, it is undefined when the denominator is equal to 0. So in an original fraction with just numbers, you can't divide stuff by 0, and that is a issue due to the limit of that, I guess, number. But in the function, it's the same thing. So when you have a rational function where the denominator is equal to 0, the limit is undefined. And that is a function of how limits exist and how limits work. I won't be getting into too much detail about that, but that's a key to figuring out the domain of our function here. So the junior tutor says, with that in mind, when the denominator is equal to 0, it is undefined. The domain of a rational function is a set of all real numbers that make the denominator non-zero. So to find the domain of a rational function, we have to figure out the cases where the rational function, the denominator of it, is equal to 0. So that's the key to this, okay? So then also the junior tutor expands, saying the range of a rational function can be found by graphing the function or by finding domain of the inverse function of the graph, okay? And then the junior tutor uses an example, and we'll go through the example now. All right, so the example here is that we have f of x. Okay, ignore this. This is just an example of this. Okay, so let me just draw another line here. Okay, so f of x equals x minus x squared minus 4. Okay, so we're going to find the cases where the denominator is equal to 0, and that will help us find our domain. Okay, because the domain of a rational function is all the real numbers except where the denominator equals 0. Okay, so to find the domain, we need to set the denominator equal to 0. Okay, so we're going to say set denom. All right, that's the short form to equal to 0. Okay, so we have x squared minus 4 equals 0. And we're going to do a quick factoring here. So it's x plus 2 times x minus 2. Great, equal to 0. So we have two values of x that will make our denominator equal to 0, which is plus 2 and minus 2. All right, great. So now we know the values of x that will make our denominator equal 0. So now what is our domain? So our domain is going to be x belonging to all real numbers except for x cannot equal -2 or +2. Okay, so that's going to be our domain. So we realize the fact that the rational function here, this is not the graph of this particular function, it exists on all real numbers except for when the rational or the denominator equals to 0. So in this case here, where the junior tutor wrote, when x equals -2 or +2, you see here that the function from leading from the left side or the right side is going to positive infinity. But the function leading from the left side approaching -2 is going towards negative infinity. So this is why we have an undefined value here. And the same with this one here too. Okay, so the range, we're going to do the range too here. So to find the range, we're going to do the inverse function here. So we're going to switch x and y. So x equals y squared minus 4. I'm looking at this already, and this is going to be a mess to actually isolate for y. So we're going to take the visual method again, and we're going to look at our graph here provided by a junior tutor. And the reason why this is hard to isolate for y is that we have to get rid of this rational function first, and it's going to be a whole, it's going to be very difficult for us to do that. So we're just going to use a graph, and we're just going to visually identify what the range is, okay? So our range is from -infinity to -2 here. So you can see here that at -2, there is no value here. So our range is -infinity to -2, -2 to 2, and 2 to positive infinity. So in fact, the range would just be -infinity to positive infinity. Yeah. Our asymptotes x equals positive -2. Thus, our range will be from -infinity to -2. Okay, so there's an issue with the statement here. So the range would actually be from negative infinity to infinity. And that's because you can see here that the range is measuring what are the possible values of y, and we can see here that this graph is always going to be trending from negative infinity to positive infinity up here, right? And it's also going to be close to 0 too, so it's the whole real value here. I don't know what she means or what they mean by this, but I do not think this is correct actually. Because if we visually evaluate this graph here, we can see that the range spans from negative infinity to positive infinity, and it also spans near the decimal point numbers too here. So the range would actually just be all the real numbers. So actually this solution is partially correct. So yeah, my last comment for this is that you guys can try to isolate for this and try to find y inverse and try to find the domain. It's very difficult to find that, but I would suggest looking at the graph itself and evaluating what the range is from the graph. All right.